the board, and he just his mask was good.
Yeah, the men.
Yeah, broken nose is great. And was like, whoa, oh wait, no. It's something close.
They always drop their sticks and it's like, why are they just random sticks along the ring? I know, and it's like, my sister kept thinking, why are there sticks on the floor? I'm just like, do I look like a professional hockey player? Have I ever played this game?
You know it's going to be good. They do, they sort of break their sections.
Like, you'd think they make the stick open, like some guy wouldn't shoot out one of the group games. And as he's swinging, it falls apart. He doesn't even hit the cut, it just falls apart. He's like, well, it's obviously really damaged. No. Come on, pick your game.
Oh, I finished that today.
Wait, what are you doing?
I've finished it.
You don't need detail, just use it now. But look at it. Try it.
Yeah.
This table's really wobbly.
Yeah, but you
That table's
Yeah, I think so. Yeah, I'll walk there.
just watching you, Toby, and especially you, Toby. I find that the initial one keep going. Sorry, keep going. That's 5 to 8. 5 to 8. Well, given that everything is done in miles, apart from someone tells you they're going and you want to know how many miles an hour they're getting.
A swimming pool is basically
You need more spice.
it might be a pet
What? Alright.
What all of this is?
very huge.
I think he just wanted to get rid of
We just have some stuff now, right? If he comes in, he's not allowed to come.
I got one, I got multiple.
No, tell you if you like
They have to be in a designated class. Well, no, like,
Went away and they were like, they died.
So they actually think straight to the
Hello everyone. Hello everyone, welcome back. I hope you all had a wonderful half term. Today we're going to talk by Jacob on the topic of string theory, along with his accoutrements of strings and alternate items. And so without further ado, I will hand over to him. And I hope it will be really interesting.
In 1919, a German guy called Theodor Kaluza, he made an extraordinary and bold proposition, seemed completely mad as well. He suggested that there were more than the dimensions that we know of. I can move this way, I can go up and down, that's the 3 spatial dimensions, and then we've got the time as well, so that's the 4 dimensions that we're used to. He suggested there are more than that. To explain this slightly mad idea, let's go back a few years. In 1907, Albert Einstein had just finished his theory of special relativity, that is, that time is not fixed, and that when you go faster, mass increases. And Einstein, his next challenge, he decided, was to try and explain gravity. A few hundred years earlier, in 1686, Newton published his Principia, and he gave us his famous equation of gravity. You don't need to understand the equation, but basically he said that there's a law that defines gravity, that the force you feel because of gravity is proportional to the mass of the objects and inversely proportional to the square of the distance away those objects are. And so Newton said this equation, it gives us good values, it gives us accurate values, and he could predict the orbit of the Earth around the Sun, he could predict the orbit of the Moon around the Earth, he could even predict the motion of the proverbial apple hitting his head. But he couldn't explain why it worked. So to try and help explain, I'm going to say, let's imagine that all of our 3 spatial dimensions are sort of condensed into one. So we imagine that all of the spatial dimensions are just going to be represented as one dimension. So Einstein said that, okay, so this grid, which kind of goes like this, is all of our dimensions. So Einstein said, if there's no mass, there's nothing there, then space is flat, or space-time is flat, which is both space and time. Now, if we introduce a mass, like this, space-time becomes curved. And this solves quite a lot of problems. So this explains how gravitation works. Instead of saying, oh, there's a force that pulls it, we can now say, well, if we've got a satellite going around the Earth, it kind of follows the path that's at the same height around the Earth. And it's quite a nice visual way of representing it, but remember that this grid represents all of the 3 dimensions, so it's very hard to visualize in the three dimensionals. What we're actually doing here, by curving it, is saying, well, this is a 4th dimension. Now, so Kaluza thought, okay, so we've done that for the gravitational force, so what about if we try and explain another force with it? And the only other force at that time was the electromagnetic force. So he said, okay, well, let's say if we introduce, let's say there's another dimension, and let's say that the electromagnetic force is caused by fluctuations or sort of curving in this extra dimension. He did a bit of maths, and out popped a very known equation to him, which is the one that describes the electromagnetic force. It seemed to work. He actually ran around his house shouting victory at this point. And he believed that he'd come up with a theory for everything. There's a few problems with that. So, I mean, the first obvious question is that if there's this extra dimension, why can't we see it? Why can't I see that extra dimension? Well, in 1926, a man called Oscar Klein came up with a solution to this problem. He said, okay, let's say that there's 2 types of dimensions. There's the big extended ones, which we're used to. I can walk in those big extended dimensions. There are 3 of those in our kind of perception. And then there's another type of dimension as well. And those dimensions are tiny and curled up, and we can't see them. Now, it seems a bit of a strange idea at first, so I'm going to do a bit of a demonstration. And I need 2 volunteers, please. 2 people come on. Okay. So I'd like you to hold this piece of string here. And I'd like you to come over here and hold that piece of the end of the string. Okay, if you hold it up so everyone can see it. Now, okay, so for those of you at the back of the room, or possibly if you were at the other end of the country over there, if you looked in the distance, this seems like a one-dimensional object. It's only got a length. If I was to stand on this thing and do a tightrope walk, I would only be able to move either that way or this way. I can't go in any other directions. This is a one-dimensional object. We imagine that has no thickness. Okay, now, imagine we have the thicker rope. Okay, thank you. Don't run away yet. Actually, yeah, you can run away. Imagine we've now got a thicker rope. We've got a thicker rope here, but for even better demonstration, I've made a rolled up tube of cardboard. I'd like to imagine that this is a rope. So, and now what we've done is we've got our binoculars from over there, and we're looking in detail at the rope, the line here. And we notice that there are some ants on it. Now, from the ants' perspective, if they walk along here, they can not only walk this way, but they can also walk around the rope as well. Suddenly, we've got an extra dimension, because they can, to define its position, we not only have to say, oh, it's this far down here, we also have to say how far around it is as well. So this is kind of a fairly basic analogy of having a sort of hidden dimension, and we can't see it usually because it's too small for us to see at the present levels of sort of how far we can see. So if you have to imagine that in every single location in the universe, there are curled up dimensions, like there's a curled up dimension. So this is one extra dimension. You have to imagine that all of these points, these are infinite number of points, and they exist everywhere in all of our dimensions. Remember that this grid represents all of the spatial dimensions. So at every single point, there's like a loop. And so now to say where I am, I have to say this way, this way, this way, and I also have to say how far around I am on this. Okay, so that's one extra dimension. And this is kind of an idea of 2 extra dimensions. So I have to say right, forwards, upwards, and then also our distance around this way and our distance around this way. Okay. So that's kind of a fairly odd idea. I'm just going to take a second to give a quite useful thing that extra dimensions give us, which is a kind of concept of things that we don't understand. Okay, so in quantum mechanics, we talk about things in a kind of probabilistic way. We say, okay, well, there's a certain probability that I'll see an electron. We can't actually say that there is an electron there and it's moving with this velocity. It's actually impossible to say that. And this comes up with a kind of new idea. So, this is, imagine that this is what we can see. So they've got this line here, and along this line these lights appear. And we're scientists, so we try and come up with a kind of formula that says, okay, well we want to know when there's going to be a red light. It's quite important that we know there's a red light. But we looked at it for a long time and we realised that we can't actually say exactly there's going to be a red light here. We can only say with a certain probability we might see a red light. Now, suddenly we think about an extra dimension, and now our field of view changes, and now we understand a lot more about the situation. We can suddenly predict with complete accuracy when we're going to see a red light, so when this ball crosses the line. And suddenly we've changed the problem from being something that we can only give a probability for to something that I can predict with absolute certainty. So with this idea, there are various people who believe that extra dimensions help us solve the problem of the uncertainty principle, if you know what it is. Okay. So now I'm going to move on to the next bit. Particle physics today is described by the Standard Model. I'm going to say a bit about this. This is quite important for what we're going to talk about later. So up here, these 6 particles here are known as quarks, and they come in 3 pairs. These are the lightest ones, the up and down quark, and they constitute all of the matter that we see around us. 2 up quarks and a down quark form a proton, and 2 down and an up form a neutron. And down here we've got an electron. This column here makes up all of the matter that we see in our day-to-day lives. There are 2 further families, like this, which are heavier and more unstable, and so we don't see those in real life, but we do see those in real life, in everyday life. We do see those in cosmic rays and in things like the Large Hadron Collider, where there's lots of energy. So these are the quarks, and then these are the leptons, and they interact in different ways. These are neutrinos, we don't know very much about those. Okay, and on the right here we've got 4 force-carried particles, or gauge bosons. And I can talk about those. We've got the strong force, and that interacts with the quarks, and that's what holds together the nucleus of an atom. We know that's very, very strong because, well, the atoms aren't going to fall apart on their own. And I'm not talking about the protons and neutrons. I'm talking about being held together. I'm talking about what's making up a proton, holding it together. So the protons don't fall apart, and that's the strong force is responsible for that. The next one is the weak force, and this is responsible for nuclear decay and fusion and things like that. And we've got 2 bosons for this. We've got the Z boson and the W boson, and both of those come in 2 different varieties. And the next one that we see is the electromagnetic force, and this is responsible for things like light and magnetism, and that's the photon. And so we know quite a lot about that, and we found that all of these 3 things come in discrete packets. They're not the ranges change, but they come in discrete packets. Now you'll notice that we've used up all of the 4 force particles from the previous slide, but there's one key force that we haven't talked about, which is, as I heard someone say it, gravitation. And what's the force-carried particle for that? Well, you'll notice that that's not included in the Standard Model, and that's actually because the Standard Model doesn't include gravity. It can't incorporate it. And if you introduce gravity, it all goes very wrong. And I'll talk about that in a second. But from that we can say that the Standard Model is not a complete theory. We know that already, but I'm just emphasising that. There are some more problems with the Standard Model too. The 4 fundamental forces, as I've mentioned, have different strengths. I've actually been doing an experiment during the course of this talk, and I've got these 2 masses. Some people were wondering what they were for. And I have come up with a very good conclusion, is that the force of gravity is very, very weak because these 2 masses have not come together and attached themselves together. It sounds like a trivial solution, but if you compare that to 2 magnets, where I can do that, that's holding it against gravity. So in conclusion, the electromagnetic force, which is responsible for magnetism, is much stronger than the force of gravity. We know that the strong force is even stronger still because, as I said, the protons aren't falling apart. and the weak force is also quite strong. I don't have such a good analogy for that because it's slightly more abstract. The reason why the gravitation force, I can notice it because I can drop this pen and it falls to the ground. But that's because we're talking about the whole world. We're talking about a whole planet's worth of mass, whereas this is quite heavy, but it's 10 kilograms. And so we can see that the different forces are very different strengths. And the second thing is that they have very different ranges. Well, I mentioned that the electromagnetic force has an infinite range. The strong force and the weak force have very, very small ranges, and the gravitation force also has an infinite range. And so why, we want to ask the question, why? Why do they have different ranges, and why do they have different strengths? And why is that difference so big between 1 and 25 zeros after it? That's a huge difference. What's going on? The second thing is that the standard model, these are the 20 numbers that define our universe. That's a joke. But it turns out the standard model, all of these numbers have been found by experiment. This is not the theory of the standard model saying, okay, these are the numbers because that's what the math says. These have been found in the Large Hadron Collider and other similar experiments. And it turns out that if you change something like, okay, the electron mass, this one here, if you change that value in the 15th decimal place, the universe can't exist, it doesn't work. And the same for any of these. If you change the gravitational constant by a tiny bit, like 25th decimal place, doesn't work. So I asked the question, well, why is it so precise, and why can we not generate the numbers from the theory? It seems like a fairly basic thing that you don't have to find the numbers experimentally, you actually sort of know what they are before. These are kind of like, okay, we've got an idea, but then we're going to fit some numbers to it because they work, which is fine, but for a theory of everything, we want to be able to know what they are with just one initial number, which we will come on to. The other thing is that if we plug in a different set of numbers, if we change a lot of these numbers, it actually still works, which is a bit contrary to what I just said, but if you change them in a particular way, the standard model still works, but you have a different kind of universe. And so even if these numbers did explain the universe of the standard model, which it doesn't, which they don't, it wouldn't explain a unique solution. And so actually it's not very good at explaining anything. Sounds a bit odd. Because that's the model that we use to describe everything at the moment, in terms of quantum mechanics. So all of the sizes of these elementary particles have been found to the closest 10 to the minus 18 meters. That's a very, very small distance. I can't visualize that, and I don't think any of you can. If you can, you're slightly insane. That's a very, very small. When you get smaller than this distance, we don't know, but our experiments are not precise enough to be able to say whether a quark is this big or bigger. And I'm not saying that they're this big, I'm saying that that's how close we know the size to. If we introduce gravity into this, all falls down. I'll come back to that in a sec. In fact, no, I'm coming back to that right now. Under the distance called the Planck length, which is about 1.6 times 10 to the minus 35 meters, that's very, very short. That's 10 to the 20 times smaller than an atomic nucleus. So we're talking absolutely tiny, minuscule sizes here. Basically what happens is that there are spontaneous fluctuations because the uncertainty principle, blah, 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 blah. Basically energy turns into electrons and positrons, and they come out of nowhere and then they annihilate. And we get this kind of, this is space-time, and it all kind of sort of goes crazy, and it's known as quantum foam. But if we've got particles, then we have energy, and if we have energy, E equals mc squared, that means there's mass. And if there's just lots of mass, there's a like infinite amount of mass in an infinitely small space, then we have a very, very large force of gravity due to a vacuum, or like nothing there, and the universe collapses. It's absurd, it doesn't work. So this is why we say general relativity, which describes gravity, and quantum mechanics, i.e. the standard model, do not fit together. So we need a different theory. We need to come up with a new theory. So let's change things a bit. So this is our particle. We imagine it to be a point particle. There is no sort of thickness to this. It's a zero-dimensional point. So it doesn't have any thickness, no length, no height, it's just a point. Now let's say instead of it's a point, it's actually they're actually not. These are not elementary particles. Let's say they're actually all composed of the same kind of thing, and they just have different properties because of the way that it works. Let's say they're all actually one-dimensional filaments vibrating. This is what is known as a string. The strings are so small that at our present magnification levels, we see them as points. We would see them as strings, but we can't get down to see that fine detail, so we see them as points. Using this idea gives some very astonishing results. Incidentally, it's also the one that Sheldon Cooper is always researching about in the Big Bang Theory. So, to try and explain this, how this works, we're going to consider a violin string. So the string is a fixed length, it's like this, and if I pluck the string, I hear a noise. It's fairly obvious. But if we think about that, that's because we've kind of created a sort of potential energy by plucking it, and then the energy sort of knocks the particles knocked together, and I hear noise in my ears because the particles are knocked together and cause vibrations. There's energy, that's the point. If I pluck harder or I pluck in a different way, I'll get a different amount of energy. So maybe the frequency changes or the amplitude changes. There are equations that tell us that frequency is proportional to energy, and we can also work out that if you pluck it harder, obviously it's louder, so there's more energy. That's fairly self-explanatory. So there are different ways that it can vibrate, and they have different energies. So we know that amplitude and frequency are related to energy. Now consider a fundamental string, which is that loop that we saw before. If we look at Einstein's equation, E equals mc squared, comes up a lot here, we know that energy is equivalent to mass. So if the string has more energy, i.e. it has a greater amplitude or has a different frequency or something, then it corresponds with a particle with a greater mass. This seems like a very strange idea. I've got some fundamental strings down here. So this particle here has a greater mass than this particle here. And that doesn't seem very obvious just by looking. So, you just said it was vibrating fast or different frequency or something. But that's a fundamental thing. Energy is really proportional to mass. If we have more energy, then we have more mass. And if the fundamental particles themselves vibrate in a different way, then that means we have different particles. So now we see a way of connecting these strings, which are all identical, to our 16 fundamental particles that we saw before. Using a similar idea, we can suggest that different types of vibration, different kinds of frequency, generate different properties, so like charge and like spin, and all of those different, and it sort of describes how it interacts. Or we can look at it in a different way. We can say, if it's got a different property of its oscillation, then we can say that it interacts with a field in a different way. So if this sort of change in frequency causes a difference in mass, then it interacts with the gravitational field differently. If it's a change in charge, then it will interact with the electromagnetic field differently. In addition to that, string theory always comes up with this particle which has no mass and corresponds perfectly with what we think would be causing gravity, the graviton. And so suddenly we've got a quantum theory, individual items, which automatically bring gravity into the picture, which is what we're looking for. So, fine, sorted it. But first, we have to work out exactly how these strings vibrate. If we can work out how they vibrate, then we can sort of see, that will automatically generate all of the different particles that we can possibly have. So, and it turns out the only number that defines how they vibrate is the tension in the string. Now, various estimates put it to be roughly 10 to the 39 tons. That's 1,000 billion tons. It's quite a lot of force. Lots of tension. So as I said, if we want to find out how strings correspond to different particles, we need to talk about how they vibrate. We need to calculate how they vibrate. And before, right at the beginning of the talk, I talked about how Kaluza and Einstein thought about an extra dimension to try and describe a force. Well, what if we do the same thing here? If we use extra dimensions to describe each type of oscillation, and then we use those to project sort of different properties of the particle it creates. So, turns out that we need about 10 dimensions. 9 space dimensions and 1 time dimensions. Actually, there's another theory that suggests that we need 11 dimensions, 10 space dimensions and 1 time dimension. So the maths is consistent. So if we work that out, that means we've got our 3 extended dimensions, which we were talking about earlier, and the rest must be curled up. So how do we visualize a 6-dimensional space? I can only see 3, you can only see 3, we can move in 3, or maybe we can move in more, we don't know. I'm talking about spatial dimensions, it's obviously time as well. So how does 6 fit together? Well, we saw how 1 and 2 dimensional spaces fit up, but that's the maximum of what we can see. There's a certain type of shape, or a space, called a Calabi-Yau space. And they look like this. This is a 2D projection on a screen of a 6-dimensional, or actually could be any dimensional space. They're very, very complicated. I don't understand them at all. It turns out that there are about 10 to the 500 of these spaces, different shapes. 10 to the 500. To give you a scale, if we counted up all of the elementary particles, that's those 16, in the universe, total, that's about 10 to the 90. 10 to the 500 of these. So how on earth are we going to choose which one is relevant to our universe? Some of these shapes even describe a complex number of dimensions. What does that even mean? It's ridiculous. So this is a visualization here of how these extra dimensions would fit in space. And I was looking at this earlier for about 10 minutes, and it's like slightly transfixing. It's just really weird. They're kind of rotating, but then they change as well. So this is, remember, this represents all of our 3 spatial dimensions, and these shapes represent the extra 6 that are curled up. It's absolutely mad. So I'm just going to leave that up there for a bit so you can ponder it. Okay, so string theory also fixes a few more problems. So when we were talking about very small scales, we heard about quantum foam and how the particles, we kind of get random particles coming in and out of existence at kind of free will. Not free will, but that kind of idea. So now instead we can kind of see this in terms of strings interacting. There are some just strings that are, they sort of change form, and we see a particle popping out instead. So I'm going to have to tear you away from the mind-boggling animation. So this is what happens, an electron, this one here, and its antiparticle, the positron, come together, and they don't work together, so they annihilate. They just turn into a flash of energy, a gamma ray, or an electromagnetic wave. And then at another point, they can also regenerate themselves and come back to an electron and a positron. So, what happens if we want to describe that using strings instead? Okay, so there are... so imagine these are strings. This is our positron. Oh, use a different colour. This is our positron, and this is our electron. So that's separate. This is our electron, and in case you haven't realised, this is the motion of time, like this, and that's the same in that. So time goes along that way. So now we have our. I mean, obviously they're going to be these strings are going to be vibrating in 10 dimensions. So we can't really visualise that, it's very complicated. So we've got our electron and our positron, sorry, other way around, electron and positron, and they come together, and as they meet, they kind of come together and they form a different string. And this is going to vibrate in a different way from this, which is also going to be vibrating in a different way from this, because they're different particles, and they have different charges, and then this is a gamma ray, or electromagnetic wave, or actually it's going to be a photon. So now suddenly, using one type of shape rather than using some random symbols like an electron or a positron, we can just demonstrate it in terms of 2 strings, and they come together and they form a different type of string, and then this is kind of continuing down here, and then they can split apart again. So that's quite powerful. And it also explains a very useful idea in physics, which Will talked about, which is that we can't talk about a time as being a kind of defined point. Me and you, if we're moving at different rates, I can't say that the moment when this pen hits the floor is exactly the same as when you say it hits the floor. But hang on a sec, in this theory here, we're saying that these are points, and they hit together, and they, at that precise moment, they form a photon. But that doesn't work, so we just said we can't say that they happen at a single point. So this is kind of not right. And so what we have to come up with is saying, well, we don't actually know where they are, and so we don't know the exact points. It's kind of all fuzzy. If you think about it in terms of strings, a quite impressive thing comes up. So this is the combination of, this is like the top line there. And what's happened is that they've drawn on, they've kind of all joined these all up, okay, like this. And then they join together here. And so you can see how they kind of, this kind of works. And this is called what we call a world sheet, or a time map, or whatever you want to call it. So at this point, so obviously these are formed up of, this is actually not, this is not a particle, this is the kind of combination of lots of time. So from my perspective, this point here is when these strings touch and form one different string. And so that's the point. Now, these diagrams are not drawn very well, but basically, from your perspective here, this is your perspective, you can see there are different angles. Remember that space, all of space is demonstrated by this dimension, all of time is demonstrated by this dimension here. So it's a kind of bit of a weird diagram, but so if the angle of this sort of vertical thing is different, then that means we're a different perspective, a different frame of reference. Now suddenly, the reason why we can't see these two events happening at the same time is because from our sort of angle or our perspective, they actually don't happen at the same time, because from our view, the strings don't combine at the same time. It's a kind of subtle difference, but that means that we don't have to say, oh, we don't know what's happening. It just means that we have different perspectives on what's happening. And I think that's kind of better, because if you just say, well, we don't know because we don't know because we can't know, well, that's a kind of bit rubbish, isn't it? So that solves the kind of, that kind of circumvents the uncertainty principle. It's actually explained within the theory itself. So, oh yeah, so that's the same as what I was talking about before. Is string theory right? It was the question you all actually came with. We don't know. And we don't know whether we'll be able to know. The energies that we need to test the predictions that string theory kind of makes are so high that it's completely unforeseeable. It's just not really possible that that's going to be, that kind of energy is going to be created on Earth in an experiment like the Large Hadron Collider. It's not feasible. And what happens when we need higher energies? We look at cosmic rays, but they're also not energetic enough. So kind of we can't test it. So you might ask, so what's the point of the whole thing? Why have we bothered doing this if we can't test it? Well, I think that even if it doesn't work as a theory of everything, I mean, we don't know. I don't think personally that we'll be able to know it ever. That's probably a very sort of sweeping comment. I'm sure there'll be something that causes it to. It's one experiment that kind of might explain it or give proof, is that if there's a sort of particle collision and we see less energy afterwards than we did before, then that might suggest that that energy's gone to a different dimension. And if we kind of see that there might be 11 dimensions, that could be a kind of indicator that it might be right. But it could be a different thing that also has 11 dimensions. So can't really say very much about that. And people get, as I was doing lots of research for this talk, I looked at lots of online forums where physicists kind of exchange ideas, and they have such heated arguments. It's incredible. Like they get so sort of angry at each other for saying, "Oh no, string theory can't be right. What are you thinking? You can't be a physicist if you believe in string theory." Literally that much. Like they just dispute like all of their education. You're not a physicist if you believe in string theory. I don't think it matters that much, to be honest, whether it's correct or not, if we can't test it. But I think, as we've seen, like this thing about sort of points of view in terms of like time and space, I think that's a very powerful tool. And just as chemistry is not a theory of everything, but it's still a useful tool, we can predict everything. And quantum mechanics is a very useful tool, and it predicts certain things at certain scales. I think string theory is a very useful tool. So even if it does not describe the universe and everything within it, then I think it's still useful in its own respective field and situation.
elementary particles. Why did you miss out the Higgs boson?
Oh yeah, I thought you might ask that. That because it isn't in that picture, and that was a nice picture.
Okay.
So yeah, we've got the Higgs boson, which is kind of a separate thing from these. So these are forces. The Higgs boson doesn't describe a force; it describes a field kind of thing. I don't really understand it. Basically, the Higgs boson suggests is a kind of way that things gain mass. The gravitational field is more like a way that interacts with the mass that's been generated. So it's separate. It's a kind of different category from any of these, and it wasn't on that picture, so that's why it's not. Anyone else? Yeah.
If the extra dimensions exist at every point, every possible point in the extended dimensions, then why are there only a finite amount of Calabi-Yau spaces in the universe? Wouldn't that imply that the extended dimensions are discontinuous? Because you can't...
Yeah. So I do understand your question. I'm just coming up with a good way of explaining it. Okay, so imagine these. If we consider so instead of considering these as individual loops, we consider them as a roll-up across cylinder. Okay. So it's like this instead. It's not. The point is that they're not discrete. They're kind of continuous, but we can't show continuous. Like I understand what you're saying. It's kind of hard to do. This is a problem with the idea of extra dimensions. That it's very, very hard to visualize without kind of stepping down to lower dimensions. There are so on a sphere. Is that a sphere? On a sphere. Also on a circle, we can describe that as a one-dimensional object.
Yeah.
By saying, well, you can only go around it like this. You can't go across. If you turn that into a sphere, we can say that's a two-dimensional surface because you can only go this way or this way. It's very hard to visualize more than that because we're kind of describing a higher dimension, and so it's very confusing. The idea is that these are continuous dimensions, but they're just so small that we can't see them. I haven't really answered your question.
So what I'm saying is, because there are a finite amount of Calabi-Yau spaces,
Yeah.
could you get to a point halfway between two and say that the other dimensions don't exist in those places because there's not a Calabi-Yau space there?
Right. Okay. It's really hard to answer that question. Basically, the Calabi-Yau spaces, because they describe a very large number of like they can describe any dimension, number of dimensions. This is what I understand. I mean, if you want to learn more about it, then you can look at this book, Elegant Universe by Brian Greene. It explains everything to do with string theory. I don't understand it. And basically he says that there is actually progress in choosing which Calabi-Yau space there is. And it is partly fueled on the number of dimensions that it could represent. But the problem is that we don't know how they represent the dimensions. So if there's a point that we can kind of say, okay, well, this kind of character means that suggests there are this many dimensions, that would be really useful. But we're not at that stage yet, so it's very hard to say whether the Calabi-Yau spaces would say something about the dimensions or vice versa, because we actually don't know how it represents it very well. There are some various kind of ideas, but not any sort of concrete theory as such. Does that make sense?
Go on.
I haven't really answered your questions. Felix?
Is there any kind of link to kind of fractals or fractal spaces? Because you've talked about all the sort of discrete number or amount of dimensions curled up in circles and spheres.
Yeah.
But is there any kind of link to kind of fractional amounts of dimensions?
So I think of a sort of similar question. Can I answer a slightly different question?
Yeah.
If that's okay. So he's kind of asking, I think he's kind of asking, I don't really know very much about fractals, but there is an idea, this question that could be asked is whether the strings themselves are fundamental. So can you look at these strings and are they going to be composed of smaller things? Could they be composed of smaller strings? Which is kind of looking like fractals, which are made of the same size. Fractals are the same shape, replicated on a smaller scale or a larger scale, so it repeats itself. that kind of thing. The question, are strings themselves fundamental? Well, we can't know if strings exist or not, so whether they are fundamental or not is a slightly academic question in my view. But they could be, but I don't know. I don't really know, to be honest.
Okay.
Anyone else?
Well, and I'll say thank you very much. Can we have another round of applause for Jacob?
The masses still haven't moved, I'll just point out.
And also, on Friday, Alex will be giving a talk on ancient mathematics, which is the first in our series of history of maths talks, so everyone come to that tomorrow. See you then.
The man got something and then we're like, why didn't you think of that, Charlie? And we're like, it's all right, man. Oh my God. Everyone's saying thing of yeah, it was Charlie's, but I stole it from him. And then I gave him a long elaborate use of it. Fake him and
Would that be alright?
Yeah.
Thanks.
Nice one.
About the conclusion of quantum mechanics talk and the string theory talk is we don't know, leave me alone.
Jacob, what was the reasoning when you mentioned between how quantum mechanics and our standard model are capacity?
Okay, quantum mechanics. Let's know what is a quantum mechanics.
Yeah, no, because there are, apparently there are multiple reasons.
What are you doing?
Multiple areas where they affect.
Yeah, so quantum mechanics suggests basically how the fluctuation
You're losing so boring. It's literally every logic.
So if you've got any mass,
It wasn't. You guys weren't really having fun. You're just sitting there. Yeah, like talk. About what?
Okay.
Jonas being like,
Is this thing filming?